Welcome to this lecture on the Burger's equation. Imagine a single-lane highway where cars are moving forward at a steady pace. Suddenly, the cars in the front hit their brakes. The cars behind them are still moving fast, so they quickly catch up and bunch together, creating a traffic jam. In physics, this sudden bunching up is called a shock wave. Today, we will explore the mathematical tool that perfectly captures this phenomenon. Now that we have our highway analogy, let us dive into what the Burger's equation actually is. This equation is a fundamental partial differential equation used heavily by scientists and engineers to simulate the flow of fluids. Think of water rushing down a pipe or air moving over an airplane wing. It tracks how a specific quantity, usually the speed of the fluid, changes across multiple dimensions simultaneously, such as time and physical space. It perfectly isolates the universal struggle between chaotic steepening and calming friction. Building on that idea of fluid flow, scientists use two main versions of this famous equation. The first is the inviscid version. This version ignores friction entirely, meaning it only models how the fluid pushes itself forward until it crashes into a steep shock wave. The second is the viscous version. This one includes a friction-like term called viscosity. You can think of viscosity as a mathematical shock absorber that works to keep the wave smooth and prevent it from breaking. We will start by focusing on the inviscid version. This brings us to the mathematical form of the inviscid Burger's equation. The equation states that u sub t plus u times u sub x equals 0. Here, the variable u represents the velocity of the fluid. The term u sub t is the rate at which this velocity changes as time moves forward. The term u sub x is the spatial derivative, meaning how the velocity changes as you move along the physical distance. The most important part is the u sitting right next to the spatial derivative. This multiplication means that the speed at which the wave travels is equal to the height of the wave itself. Taller parts move faster than shorter parts. Before we move on, let us see this with a concrete example. We want to solve the inviscid Burger's equation given an initial starting condition where the velocity is exactly equal to its position on the line. To solve this, we use a technique called the method of characteristics. This method works by finding special, hidden curves in the fluid along which the complex partial differential equation turns into a very simple ordinary equation. We first define the physical speed of our special characteristic curve, which is exactly equal to the fluid velocity. Then, we note that along this curve, the velocity of the fluid does not change at all. Continuing with our solution, because the velocity does not change along the curve, its value at any future time is exactly the same as its value at the very beginning. We lock in this starting velocity. Next, we calculate where the curve actually goes by integrating our speed equation. The current position is equal to the starting position plus the distance traveled, which is the constant speed multiplied by time. We then rearrange this to solve for the starting position, allowing us to link the past to the present. Finally, we substitute this starting position back into our velocity equation. Now we are ready to find our final answer. We need to gather all the terms containing our unknown velocity variable on the left side of the equal sign. We do this by adding the term containing time to both sides. Next, we factor out the common velocity variable, leaving it multiplied by a simple time factor in parentheses. Finally, we divide both sides by this time factor. This gives us our final solved expression. Physically, this tells a beautiful story. As time gets larger, the denominator grows, causing the overall velocity to shrink and the wave to stretch out smoothly. Now that we have solved a smooth case, let us look at a dangerous scenario where a shock wave actually forms. We use the same inviscid equation, but this time our initial condition is negative x. This means fluid is rushing inward toward the center from both sides, setting up a massive collision. We start with the same position tracking equation we derived in the first example. We substitute our new dangerous initial condition into the equation. This clearly shows that the distance traveled is working against the starting position. We then factor out the starting position on the right side. Continuing with this dangerous scenario, we rearrange the equation to solve for the starting position by dividing the current position by the time factor. We then substitute this starting position back into our initial velocity rule to get the final velocity equation. Notice the negative sign and the denominator. As time gets closer and closer to the number 1, the denominator gets closer and closer to 0. In mathematics, dividing by 0 creates an infinity. Physically, this means the slope of the wave has become a perfectly vertical wall. This exact moment at time equals 1 is when the shock wave forms. To truly understand this violent crash, let us look at a visual representation of the wave steepening. On the horizontal axis, we have the physical position, and on the vertical axis, we have the fluid velocity. The first curve shows the wave at time 0, starting off smooth and gentle. By time 0.5, the taller parts of the wave have traveled faster than the shorter parts, causing the peak to lean forward. Finally, at time equals 1, the peak catches up to the bottom, creating a vertical drop. This perfectly matches the mathematics we just solved for the shock formation. Now that we have used this formula and seen its effects, let us understand where it comes from. To understand the origins of the Burger's equation, we must start with the basic rule of the universe called a conservation law. A conservation law simply states that stuff cannot just disappear into thin air. If the amount of water in a section of pipe changes, it must be because water flowed in or flowed out. We can write this rule mathematically by looking at how the density of our fluid changes over time and how its flow changes over space. This brings us to the mathematical foundation of our model. The conservation law is written as u sub t plus the spatial derivative of f equals 0. In this foundational equation, the symbol u represents our conserved quantity, which in this case is the velocity of the fluid. The symbol f represents the flux, which is a measure of how much fluid is passing through a specific point. The fraction shows the gradient of the flux, meaning how the flow changes as you move along the physical distance x. If the flux changes across space, the velocity must change over time to compensate. Let us now derive the inviscid Burger's equation from this conservation law. For our specific fluid model, we make a very specific assumption about how the fluid moves itself. We assume that the flux is proportional to the square of the fluid's own velocity, specifically 1/2 u squared. This specific choice is what makes the equation non-linear. To put this back into our conservation law, we need to take the spatial derivative of our new flux term. We do this by applying the chain rule from basic calculus. The derivative of 1/2 u squared brings the 2 down, cancelling the half. Continuing with our derivation, after cancelling the half, we are left with the velocity u multiplied by the spatial derivative of the velocity. This resulting term is the mathematical engine that drives the wave forward and causes it to steepen. We can now substitute this back into our original conservation equation in place of the flux gradient. This substitution gives us the final result, the famous inviscid Burger's equation. We have successfully proven how a simple conservation law combined with a squared flux assumption leads directly to the mathematical model of shock waves we explored earlier. You can now see exactly why the wave speed depends on its own height. So, we have proven how the inviscid equation works. But what about the real world? In the real world, fluids have friction, which prevents them from forming perfectly vertical, infinitely sharp shock waves. To model this, we add a term to the right side of the equation to represent this internal friction. This creates the complete viscous Burger's equation. The new symbol nu represents the kinematic viscosity, which is just a fancy term for the fluid's internal friction or thickness. The second derivative term mathematically represents diffusion. As the left side tries to steepen the wave into a sharp cliff, this new right side constantly works to round off the edges and keep the wave smooth. We have covered a lot of ground today, so let us review our key takeaways. The Burger's equation is a beautiful and essential mathematical model that describes how waves travel, steepen, and dissipate. It captures the fundamental competition between a wave's natural tendency to bunch up into a shock wave and the fluid's internal friction trying to smooth it out. By mastering this single equation, you have unlocked the core principles needed to understand complex, real-world flows in aerodynamics, acoustics, and traffic engineering. You now have the mathematical vocabulary to describe how a gentle wave becomes a destructive force.